Okay, guys, we're going to try this again. Hopefully they are helpful. But we're going to go over Chapter 7 because you guys have that homework today. Chapter 7, and it is over substitution reactions, so like S1, SN2. I'm not sure the actual name of the chapter, but we'll call it substitution reactions. And this is that point that I was telling you that it honestly gets so much, well, for me, it got a lot easier because it's just actual reactions that you're having to memorize and, like, how the reactions work. So it's, like, the actual chemistry of it. I guess we can start with naming because that's going to be, like, the easiest thing. So go with a different color. So these are going to be alkyl halides. This is like all of them, because the halide is going to be your leaving group, at least for everything that you guys do here for the most part. So when we name them, let's underline this little section. So you have the common name and then the IUPAC name. And this is what made it easier for me to remember. So for the common name, it's the alkyl group. So whatever number of carbons it is, you turn it into an "-il" because it's the alkyl group. And then the halides. So if you have, let's say, something like this. Right? One, two, three carbons. So it's a propane, but we're changing the alkyl group to "-il. So this section needs to turn into an "-il. So it's propyl. And then this is our, why did it do that? This is our halide, and it's iodine. But we're turning it into a halide. So normally it's iodine, right? But halide. So this part, this is the halide. This part we turn to ide. So you've got iodide. So the full thing is just going to be propyl iodide. Hopefully that makes sense. And then for the IUPAC, as some call it, it is a haloalkane. So if you look at the setup in the common name, you start with the carbon group first, the alkyl group, and then you do the halide, or the thing attached to it. But for IUPAC, it's going to be the halo group first. So if we have the same, well, we'll do a different example. So if we've got something like this, right? This is only 2 carbons. So our alkane group is ethane, right? And then our halo group is iodine. So when you combine them, it's just the halo part. And so a lot of it sounds weird. But the only way I can explain it is like how would it sound the best. So we've got ethane and we've iodine ethane, right? we're going to cut it like right here. And we're going to turn it into iodoethane. So that's how it goes for naming. It's not that hard. After I go through just the chapter in general, we'll go through the homework, and I'm sure there'll be some naming examples that we can work through. I'm not the best at coming up with my own examples, but that's kind of the concept when it comes to the naming. So common is going to be an alkyl halide. So you go with the carbon group first, and then you name the halide group or the halogen group. And then IUPAC is going to be halogen and then alkane group. So the iodo comes first and then the carbon comes last. Like the carbon containing group is last. Let's go with naming the parts of our reactions. Naming reaction items. So for this, all SN or substitution reactions are going to have a nucleophile, which attacks positively charged ions, right? Because it loves like the nucleus of an atom, and the nucleus of atoms has the protons and the neutrons, right? Neutrons are neutral, protons are positive, so they love the positive charge. Attacks positive charge. Break it down. It loves the nucleus, and the nucleus contains protons, which are positively charged. Nucleophile is commonly, like, I don't know, at least when I took his class, Mayer used to do it like this. That was its shorthand. It has extra electrons and it's negatively charged, so it's going to love a positively charged ion. So you'll have your nucleophile, and if you have a nucleophile, you've got to have an electrophile, its counterpart. This is attacked by the nucleophiles. Right, it's the counterpart. So whatever the nucleophile is searching for is the electrophile. It's got a positive charge. Did I spell that wrong? Twice. Positive charge. Oop. Is positively charged. So, typically it's going to be like a carbon. And then lastly, you have your leaving group, your deserters. The leaving group is a very, very weak base. The weaker the base, the better it is. How do I write this, though? Atom leaving the compound. The weaker the base, the stronger the nucleophile. So what do I mean? Typically, when you see leaving groups, it's going to be like a halide, right? So let's think of what our strongest acids are, right? Our strong acids. We've got hydrochloric acid, hydrobromic acid. I think hydroiodic acid is as well. Yeah. And then really I'm only going to work with these three because they're going to be the most common ones you guys see on the exams. It's going to be like these three atoms. But so if these are our strongest acids, you remember that these are considered the conjugate base, right? So you've got, these are the conjugate bases. But as a conjugate base of a strong acid, it is so weak as a base. It's like not, it doesn't even know how to be a base. So the weaker the base, the stronger. Oh my gosh. Guys, what did I just write? The stronger the leaving group. Okay. So the strongest leaving groups that we're going to see, and I'm going to shorthand it, leaving groups. Strongest leaving groups is like chlorine, bromine, and iodine. Those are going to be the most common ones you see also. So when we see this in like a reaction, when we see all three of these put together in a reaction, we've got R bonded to X, right, plus a nucleophile. What are you? Sorry about that. Obi got into something. You got your nucleophile. And it's negatively charged. And that will give you your R group now bonded to your nucleophile. Plus your leaving group just kind of floating around. This is going to be your electrophile. This is a leaving group. Your nucleophile. Oh, okay. So how this works is that these electrons are going to attack that carbon. Right? It's going to do a backside attack. So I guess a better representation of it with a line would be it coming over here. Gross. Right? And then the leaving group takes the electrons from the bond, hops off, and it leaves. So this is going to be the standard equation that we see. This is what happens in a substitution reaction. Okay. Oh my gosh. Obi! Get out of here. Okay. So now we'll start with SN1. Okay, SN1 reactions. Okay. We kind of talked about these before. I think we talked about this before already. But SN1, when we talked about like rate laws and stuff, right? An SN1 reaction is, you got your constant, and it's just the alkyl halide. And it's a first order rate law because it's only relying on one substance. Because technically this will have a 1 right there to the power of 1. First order rate law. It's favored by weak nucleophiles. So that means like the bases are relatively like strong, like they're not, the weaker the base, the better. Oh no, that's the leaving group, sorry. But nucleophiles have like a negative charge, so those are also, you can think of them as bases also. Obi, get out of there. It has polar protic solvents, uses polar protic solvents. And then here's the most important thing about SN1 reactions. It requires a second or secondary or tertiary alkyl halide. So that means you've got chlorine, right? This is a secondary. Chlorine here. This is tertiary. Because the carbon that it is connected to is connected to 2 more carbons. The carbon that this one is connected to, the chlorine, is connected to 3 carbons. That makes it tertiary. So this one's tertiary, this one's secondary, right? So the reason that it requires a secondary or tertiary is because once this chlorine leaves, you're going to be left with chlorine on the outside, and you'll have these carbons, right? This will be positive cation. And then once that chlorine leaves, you got a chlorine over here, and you got a tertiary carbocation, right? So these are going to be relatively stable. So that's why this is SN1, because you're going to have an intermediate, right? Like only the alkyl halide matters because it's going to, the leaving group leaves first, and then you add on the nucleophile. And so it needs to be a very stable carbocation, otherwise it's not going to let the leaving group ditch. It's going to keep it. Let's think of an example. Well, actually, we'll just work through the mechanism. So we'll go through an SN1 mechanism so we can kind of see it. We're going to do a tertiary just because it's the easiest to see. So we've got a tertiary, right? If it makes it easier for us to see. This carbon that's connected to the chlorine is connected to 3 more carbons, right? Okay. So we're going to put it in like acetone and water. Water is polar. So these are polar protic solvents going on here. first step is literally just going to be the chlorine leaving. This is step 1. Chlorine leaves. So now you've got a carbon connected to a CH3, another CH3, connected to a CH3, and it's got a positive charge. And then you've got, chlorine's still in the reaction mixture. It just left the compound. And you've got chlorine, who has a negative charge now. Then, when we look, we had our reaction mixture, right? We had the water, H2O. Oxygen has its lone pairs. These lone pairs on oxygen are going to be what attacks this carbon. Okay, so then this is step 2. And then the SN1 mechanisms are going to be like multi-step processes. Sometimes 2, sometimes 3 steps, it depends. But SN2 reactions are pretty much going to happen like all simultaneously. But we'll get there. We'll just finish this first. So the oxygen connects to it, right? So then now we've got that carbon with the CH3s, the tertiary, blah, blah, blah. CH3 is now connected to an oxygen who is connected to 2 hydrogens, right? But this oxygen has 3 bonds, so it has a positive charge. So it keeps going, right? Like we assume that we've got water in excess in this reaction, right? So it's going to continue to react with the water that we put in there. So these are going to go ahead and steal a hydrogen because oxygen likes to hydrogen bond. So now we've got carbon, CH3, 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 and only an OH. Plus that chlorine that we kind of ditched earlier. And then because H2O took an extra hydrogen, we now have H3O plus in our reaction also. These are just kind of byproducts. They don't really matter too much. We're not focused on them. What we're focused on is this guy. This is the major product, and that's how it's going to be phrased on the exam too. And he'll be like, "Oh, what's the major product of this reaction?" or blah 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 blah, things like that, right? Okay, this was the mechanism. So now we're going to go look at the transition states. So when we started here, right, that chlorine leaving, and I'll go ahead and write these in just so we see it a little bit better. CH3, CH3. Okay, so transition state is how we represent what's going on in our molecule. So we have carbon bonded to a CH3, 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 right? These bonds never changed, right? These ones right here, they never changed throughout the entire thing, the entire reaction. However, this bond to chlorine eventually broke, right? And so how we represent that is with a dotted line. So we'll have a dotted line to chlorine. And when chlorine leaves, it gains a positive charge, right? And we're looking here, it gains that positive charge, and this carbon gained negative charge, sorry. This carbon gained a positive charge. So here in our transition state, when we're kind of representing what's going on, so these bonds were permanent, they never changed. This one broke at some point. So it used to be there, and then it broke, so we're representing it with a dotted line. But we also need to represent what's going on with the charges. So eventually, this chlorine is going to gain a negative charge. and this carbon is going to gain a positive charge. So right now it's just going to be a partial charge because it didn't gain it all the way yet, but it's what's going to happen. And then we put it in brackets. That was ugly. Put it in brackets. And then we have this little symbol here which represents transition state. I don't know why that's the symbol, but that's what it is. So this is the transition state. This is the first transition state. Right? Because that's the first step that happens, and we're representing like where it's transitioning to, where it started from, and all that jazz. So then we come over here to the second step, right? And we're going to do this transition state. So again, carbon bonded to CH3, CH3, CH3. Those never changed. However, in this step, we went from being bonded to nothing over here and having a positive charge to being bonded to this water molecule, right? So this bond that I'm highlighting used to not be there. There was nothing there, but now it's there. So again, we're going to represent it with that dotted line. Solid now. Then we've got the OH2, aka H2O. And let's look at our charges. This used to have a positive charge. This one used to have a positive charge. So we're going to represent it with, honestly, two partial positives, because this went from having one to not having one. And this went from not having one to having one, right? So we're going to represent those with the partial positives, which is this little S thing. And then it's really the oxygen that has a partial positive. Okay, so that's our next transition state. And again, we're going to go ahead and block it off with our brackets. Brackets, and then we'll mark it like that. And this is our second transition state. All right, so finally, we're going to represent our last thing, right? So what happens in this step? What's going on is this hydrogen is being yanked off, right? So this used to have two full bonds, and then one of them left, and we're only left with just one hydrogen. So when we look at that, we'll do our carbon and our methyls. And then what didn't change was this bond stayed exactly the same, right? This carbon to oxygen bond never changed. It stayed there that whole time. The difference in these two transition states is only with the hydrogens. So when we draw the carbon to oxygen bond, it's still going to be a solid line. And we'll have a single solid line to a hydrogen. But to the other hydrogen, it really doesn't matter which one. I'm choosing the top one. It could have been either one. There's no way for us to really know, right? Hydrogen got yanked off. And the only partial... Okay. Where did the hydrogen go, right? We need to represent that also. It now went to this H3O plus. Used to be a part of this molecule, and then it got yanked over and is now joining this H3O plus. The water is the one who took that, right? So how we'll represent that is this hydrogen is now also bonded, partially bonded, to an oxygen who has two hydrogens, right? Okay. Now, this is the full transition state. We kind of see hydrogen used to be bonded to this oxygen and is now getting bonded to this oxygen, right? That's what the transition states are all about. We should look at it and see, okay, what bond's breaking, where did it used to be, how things are moving. So we see that this hydrogen is leaving the giant molecule to go join this water. And this oxygen is the one, this oxygen, used to have this positive charge, right? So it used to be positive and then went to not being positive. this oxygen in the water molecule used to have no charge. And then over here, it now has a positive charge because it gained an extra proton, aka hydrogen. So when we write that, this oxygen has a partial positive, and so does this one. Seal it off with our brackets. Mark it with our transition state symbol. And this is our third transition state. All right, I hope that made sense. He might ask you a question about, oh, how many transition states are in this reaction? And all you're getting is a reaction, so you kind of have to work out you have to work out how many steps are there. Each step, that's another way to look at it. Each step has a transition state, right? Because obviously there's something happening. So if you see multiple, if he shows you the full reaction, which I don't think he will, but if you see multiple yield signs, then, you know, that's a transition state. All right. So that's pretty much all I have for SN1 reactions. If you guys have any questions after watching this, go ahead and let me know. But the biggest things I can tell you is pay attention to what kind of alkyl halide you have. If it's tertiary, it's 100% going to be SN1. If it's secondary, it could be either. So you kind of have to then look at what kind of nucleophile it is, and then if there's a polar protic solvent involved. All right. And so when I talk about the type of solvent, right, polar protic can hydrogen bond. So we should probably talk about that. I'll write it off here. Can hydrogen bond. So reactions or examples of that is going to be OHs, NHs, FHs, and then ROHs, right? So in our case, we had water. We know water is polar, H2O is polar, and it's protic because it can also hydrogen bond. Okay, so then we'll move over and we'll do SN2. Okay, SN2 reactions, our rate is going to be, you've got your constant, and it's the alkyl halide and the nucleophile. And it's a second order rate law. Okay, so I want to go back over here so we can kind of see this as an example since it's already worked out. So we said that the alkyl halide was going to be the only thing that determines the rate, right? It's a first order rate law. And we kind of see that worked out here, right? So the first step is just chlorine leaving the molecule, right? It's just a leaving group leaving. So that means everything in here, like the chlorine, is going to be the limiting reagent. However much of this we have is what determines how much product we end up with, because there's only one compound in our first step. So it has to be the limiting reagent. I hope that makes sense. So if this is the limiting reagent and there's only one, this is our alkyl halide, right? The whole thing. That is why it's a first order rate law, and why the only thing that matters in the rate is the alkyl halide. So when we work over here, I'll draw out a mechanism as well, and we'll see that it relies on both the nucleophile and the alkyl halide because the reaction happens simultaneously. The leaving group pops off and the nucleophile does a backside attack at the same time. So both of them matter, like they would both equally be a limiting reagent. Because if you don't have enough nucleophile, then it's not going to backside attack. And if you don't have enough alkyl halide, your leaving group isn't going to pop off and you can't make as much. So it happens simultaneously and both compounds deal with the rate or affect the rate of the reaction. So this one is favored by strong nucleophiles. And it uses still polar, but aprotic solvents. And aprotic solvents cannot hydrogen bond. However, it can dissolve salts. All right, so it's kind of the opposite of like a nucleophile, right? So the stronger or the weaker the base, the stronger the nucleophile. But it's looking at like nucleophilicity, so how much. Let me think of how to explain this. So it can't hydrogen bond, meaning it doesn't have a hydrogen to donate. And they have like a net dipole moment. I'm trying to think of examples. So, when we talk about, like, what can hydrogen bond, how fluorine isn't on the list? Let's go back over here. We had, it is on the list, my bad, sorry. It's still reactive, but, wait. Actually, I don't even know why that's on there. Fluorine cannot hydrogen bond. Oops, sorry. Apologies, guys. Stay with me as I unconfused myself. I started talking and then I got lost. Okay, so here's how I used to write it out. The nucleophilicity, meaning like what kind of solvent it likes. So with polar protic solvents, you're going to see it increase like this. As far as like what it likes to see. And when I get examples on the homework, I'll write this down and we can like look through it, and that makes it a little bit easier. So this is with polar protic solvents. I need to nucleophilicity, and it's the ability of a molecule to donate an electron pair to form a covalent bond. So it's like the electron donating power kind of just like the strength of the nucleophile, if that makes sense. So with polar protic solvents, the strength of the nucleophile looks like this. So a iodine is going to be much stronger than a fluorine. Even though they're both nucleophiles, it's going to appreciate iodine more than a fluorine. A aprotic solvent has the opposite nucleophilicity. So fluorine is going to be number 1, and then chlorine, then bromine, and then iodine. And there's a question, I remember having a question like this on the exam. I don't have my exam with me. But I wrote down these, like, chains on the exam, and I remember it, like, coming through and helping me a lot. But when we talk about the backside attack, right? So this is when it becomes very important. Because when we talked over here about the backside attack, so this is going to be with SN2 reactions, right? This isn't really this is not a backside attack because the chlorine's off. Like the chlorine pops off, right? And then the positive charge right there, it's just going to attack it straight on, like head on. So nothing really changes. And it's because it's a multi-step process. SN2 reactions is when you have that backside attack. And it inverts the configuration. And I'll kind of like draw that out for you so you can see it. But if it hits it from the backside, it like flips, right? Trying to think of how I could explain it. I'll show you on when we do the mechanism. But it's going to invert the configuration. So that means like when you have, when we have our R and S. So if it used to be R, it's going to turn into S, and vice versa. If it was S, it's going to turn into R, things like that. Because it's going to hit it from the backside, and that's going to flip the stereochemistry. That was ugly, sorry. But that's a stereochemistry. And here's going to be the number 1, right? Requires primary and secondary alkyl halides. Because there's too much steric hindrance with like a tertiary for it to do a backside attack because it's got something surrounding it on all sides. But a primary is going to be the fastest it can go, right? So like your methyls is going to be the fastest that it could possibly go. So if we go, here's going to be our reaction mechanisms. We've got a CH3 attached to a chlorine. And we're going to add just the OH negative, right? It's got all these lone pairs. So these lone pairs are going to swing around and attack the carbon from behind. This is going to pop off all simultaneously, like it happens in unison. And then you end up with your CH3 bonded to the OH. And then your chlorine just left off to the side. And again, that's a byproduct. I'm not too worried about it. So we've only got one step happening, right? So when we do our transition state, we'll show our carbon used to be bonded to the chlorine, right? It doesn't stay bonded to it. It ends up popping off. So we've got our dotted line. And then we've got a dotted line. Let me represent this better. So this carbon is really, solid. Carbon is bonded to one hydrogen here, a hydrogen here, and then a hydrogen here. Okay. used to be bonded to a chlorine. It no longer is. And then it was not bonded to the OH at first, but now it is. So this is kind of what the transition state looks like. We've got our partial negative on the chlorine because it ends up negative at the end, and a partial negative on our hydroxy group because it started out negative and then lost that charge. Brackets, transition state. And this is what I mean by backside attack. So we've got our OH here, and it's swinging around and it's attacking the carbon from the opposite side. And so, your hydrogens are bonded to the carbon in kind of a tetrahedral, right? Because sp3 carbons are going to be bonded like that. They're planar, trigonal planar. Or sp2, sorry. sp2 is trigonal planar. But the sp3, the hydrogens are going to be on it in a certain way. And then it's going to flip them. This isn't a stereocenter. But it's going to flip, like, the orientation of it. And so I wish hopefully there'll be an example on the homework, and I'll walk through that as far as the way it's going to look when it flips the stereochemistry. But this is an SN2 reaction. Again, main takeaways, primary and secondary alkyl halides, everything happens simultaneously. The leaving group pops off as the nucleophile is attacking, happens all together. And it is polar aprotic solvents. And polar aprotic cannot hydrogen bond, but sometimes they can dissolve salts. And then the nucleophilicity, like the type of nucleophile the solvents work best with, is going to be in the opposite order as an SN1 reaction that has protic solvents. And I know I touched on the stability of carbocations, but I'm realizing now that I should have wrote it out, right? So we've got carbocations. So primary looks like this. It's basically just a CH3 with a positive charge. Secondary is a carbon connected to a CH3. Positive charge. Tertiary. Oh, I'm so sorry, guys. Let me move this chain down. This isn't primary. This is a methyl carbocation because it's just one carbon and it's got the positive charge. But it's just a methyl group, right? Primary means the carbon here is attached to just one carbon. And then secondary will be the carbon here and it's attached to two carbons. And it's got that positive charge. This is a cation. And then I'm not going to have space. I'm going to draw that down. Is a carbon connected to 3. So like on our example earlier when we had 3 CHs attached. So stability is going to increase this way. We've got increasing stability. And so, let's look at that. This carbon here has no one to share this positive charge with, and carbon doesn't like to be positive. So this carbon has one guy to share it with, but, that's not really doing a whole lot. This carbon has 2 people to share it with. He's like, okay, I'm starting to feel a little bit better. And then I forgot to draw it. Got the positive charge on this one. It has 3 guys to share it with, and it's only 1 bond away from being completely happy. So this is going to be the most stable carbocation, right? And that's why secondary and tertiary can do SN1 reactions, because the leaving group can pop off and the carbocation can be relatively stable and okay with losing the leaving group. But a methyl or primary is like fucked. It's got nobody, really there for him. So when he loses the leaving group, he's like really down on bonds, right? And so it's going to be the least stable. Secondary, it's still like not super happy, but its secondary can go either way as far as being SN2 or SN1 reactions. And then look, if we were given a reaction coordinate diagram, right? The reaction coordinate. Oops, bumping into that over there. Let's just down here. Right? So we talked about steps before, right? So when we're looking at this guy, it's got 3 steps happening, right? 3 transition states. This one has 1 step. So that's going to be kind of your giveaway. If he's giving you a reaction coordinate diagram, and if I give you one and it looks like, let's say, that. Do you think that's SN1 or SN2? Gonna pause like the teachers do. SN2. Kidding. SN1. Hope you guys got that right. Why? Because it's a multiple step. Multi-step. You can see this is an intermediate, this is an intermediate. These are the transition states. Right? It's a multi-step reaction with multi-transition states. Okay. Now, if you see one that's like this, draw it first, and it literally just looks like that. Do you think that's SN1 or SN2? Hope you guys said SN2 because that's the only other option left. SN2 reaction. Why? It's 1 step. You get 1 transition state. That's it. Okay. So that's everything I had written down as important for chapter 7. If you guys have questions over specific things I didn't talk about, message me. I'll do my best to answer and be available to you guys during your homework. Sorry I couldn't meet in person. Okay, now we're going to go through the homework together. And I cross out the answers so that way we can't see them as we're going through. So this is just naming, right? So let's look at, this is what I find the most important. It's going to be the first part, right? So we're looking for 3 CH3 groups. And heptane, how many carbons is that? 7. Good job. So I like it better when you're given the name because then you just try to orient it onto the compound. So we're going to try and number these carbons in a way that gives us 3 methyl groups. So let's just start with D. Let's find the longest carbon chain. 1, 2, 3, 4, 5, 6, 7. Okay, this gives us 1 methyl group, 2, 3 methyl groups. Cool. So maybe we're off to a good start. Okay, so it's trimethyl. On carbon 2 and carbon 4, we should find 2 chlorines. Well, actually, okay, they all have 2 chlorines. But that would be something I looked at too. So it's dichloryl. So we're going to be looking for 2 chlorines. On carbon 3, we should find an ethyl. And then the 3 methyl groups should be on 4, 5, and 6. So this should be consecutive. Okay, so let's look. Carbon 2 and 4, do we find chlorines? We have one on 4. We don't have one on 2. Now, could that be a numbering error? Possibly. So let's look. Can we number this a different way? We can go 1 here, 2, 3, 4, 5, 6, 7. Okay. Now that puts chlorine on 2, and it puts chlorine on 4. Okay. Now let's look again. We've got on on carbon 3, we should have an ethyl. Carbon 3, 1, 2. Ethyl group. Oh man, I think I chose the winner first. I tried to move backwards because sometimes it'll be like A. I think I chose the winner to start with. We'll go through them all. Okay, so this is an ethyl group, so that checks the block. And then we've got a methyl on 4, 5, and 6. Okay, guys, so far it's looking like D's our answer. Okay, let's look at all of them, though. It's so funny. Okay, we've got 1, 2, 3, 4, 5, 6, 7, 8 carbons. Now, I haven't even checked to see if this is the longest carbon chain, but right off the bat, we've got 8 carbons. Can't be A, right? We're looking for a heptane, which is 7. This has 8. So let's look at this one. We got 1, 2, 3, 4, 5, 6, 7, 8. Okay, can't be that one. Too many carbons. Now let's look at this one. I'm going to number it in a way that at least gets a chlorine on carbon 2. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, well that can't be it either. 8 carbons. So we eliminated those other ones pretty fast. Let's see. Yeah, it's D. So I know in the homework you have 3 hours. And I know in the quiz it's kind of harder to find them because you only get 3 minutes and the time crunch is rough. But you get 3 hours, so you can take your time with counting these and things like that. So, isobutyl bromide. I want you guys to tell me what kind of name that is. Is that the common name or the IUPAC name? Okay, it's been long enough. This is the common name structure because we've got alkyl halide. Let's move back up here. What kind of name structure was this one? Yes, you are correct. IUPAC. Because if we look at it, it is, I know, the actual halogen is all the way over here, but it's the halo alkane. Also, it's got like a shit ton of numbers in it. Lets you know that it's the IUPAC because it gives you the address of everything in the compound. Okay, isobutyl. Do you guys know what that looks like? You need to memorize all of your butane arrangements. And propane, because there's isopropane and isopropyl, I mean. And I think that's the only one that has also another name. But those need to be memorized for sure. So let's look. Butane. Oh, perfect. Sorry guys, I was looking for my chem notebook that had all the butanes drawn out so I don't make a mistake teaching you guys. Okay. So I'm going to draw them over here for us. We've got butane. 1, 2, 3, 4. 1, 2. Actually, let me do those in different colors for you. 1, 2, 3, 4 carbons. And then it'll be connected to like something else. Right? That doesn't really matter though. This is the random connection. Then you've got, oh, sorry, that is butane. Then we've got this, like I said, that could be connected to an R group. This is your N-butyl. When we start becoming ill, it's a substituent now, butyl. Then we've got R group here. 1, 2, 3, 4. This is called sec-butyl. Because it kind of intersects the 4 carbons, right? Then we've got our group here. Isobutyl. Strange looking guy. I don't really have a way to remember it other than it looks like a Y. Yeah, because why is it doing that? Isobutyl's a weird guy. Why is he doing all that? And then last but not least, we've got our R group. Got tert-butyl. Let's get out of my way. And I remembered this because it looks like a chicken foot to me. You know, like the little toes. Looks like chicken feet connected to the R group. So isobutyl is a weird guy. Why is he doing all that? It's shaped like a Y. Sec-butyl is intersecting the 4. And then N-butyl is literally just a chain attached to an R group. Okay, now that we know them, should be spotting much easier, right? What is this guy? Chicken feet. That's tert. What's this guy? He's intersecting a 4-carbon chain. Oops, where are we going? Sec-butyl. What's this guy? He's shaped like a Y. Why is he doing all that? Isobutyl. What's this guy? 4-carbon chain. We're pretty boring. We're just our N-butyl. What were we looking for? Iso. And then all of these have bromines. So our answer C. Correct. Yeah, I'm literally good at this. Okay. Moving on. Ooh, nice. We talked about this in the lesson earlier. What is the most effective leaving group? So, it's kind of based on basicity, right? How good of a base it is. So, as basicity? I don't know, guys. This is chemistry. I can't spell. But as basicity goes down, leaving group goes up. Okay, so now we're going to go based off of what we're seeing here. Okay, this is SO3, right? They're all going to be connected to the carbon, right? This one, This is a O CH3 3 negative. Okay. So really we just have like a negative O is what we're looking at. What is this? Hydroxide. That is a base. That is a strong base. You've got NaOH, KOH. These are strong bases. But I said as basicity goes down, leaving group goes up. So this would be like a number 1 base, which would make it a horrible leaving group. Negative CH3. Methane. Not really a good leaving group. You know, it's going to want to join something because carbon doesn't like being negative. So why would it pop off? Not that. This is, right here, we're looking at SO3, right? What are our strong acids again? HCl, HI, HBr, HNO3. Oh gosh, what are all of them? There's like it's like HClO. Yeah, HClO4. That's 1, 2, 3, 4, 5. Gosh, what am I missing? HClO3, I think, is also one. And then H2SO4. Gosh, I thought I was going to make a really good point here. This is SO3. So, we're actually going to disregard that because this is SO3. It's not the conjugate base of a strong acid. Okay, anyways, looking at these leaving groups, right? So, we're comparing these oxygens. And another thing that makes a good leaving group, let me pull up my old notes real quick. Okay. So when we talked about like the basicity, right? So having high electronegativity, large size, and being resonance stabilized, right? So we're comparing these oxygens to each other, right? Because that's where we see the negative charge. Usually, we like to see the negative charge, but he gave all of them 1, and so he's trying to see what you really know about them. A methyl is not really a good leaving group. We don't really see carbons ever leaving, right? So we're comparing these oxygens. So this oxygen, once it leaves, it's going to leave a tertiary carbocation, right? This isn't going to be a tertiary, but it has resonance because we've got double bonds, which makes it more stable. You know how resonance always trumps like a tertiary? When we look at, I don't know if you guys actually have had questions like that yet, but it'll be like which one's the most stable, and it'll be like a tertiary carbocation, or I don't know if you guys have done alkanes yet. I can't remember where that is in OChem 1. But when we looked at what's the most stable double bond, and it'll be like primary, secondary, things like that, tertiary, or, when we look at stability, resonance always makes something more stable. So even if you have if you've got a positive charge here on a carbon that's tertiary, it still won't be as stable as something like this, because this has resonance. So then you would end up with it over here, right? Resonance always trumps tertiary. So this would essentially be a good leaving group because it's leaving behind a tertiary carbocation, which is good. Like, that's pretty stable. But this one has resonance. These double bonds can ditch and move around all over. I don't know why I have this here. Sorry, guys. These double bonds can move. So it's got resonance, which is going to make it the most stable. Hopefully on your homework he doesn't give you something that hard. But that would be the most effective leaving group. Okay, good. I know what I'm talking about. Answer's A. Resonance beats tertiary in stability. And then we, talked about acids. The stronger the acid is, the more stable its conjugate base, right? And the stronger an acid, the weaker it is as a base. So if we were looking at these as acids, once, now these are the conjugate bases of acids, then this one's going to be the most stable, making it the strongest acid, aka the weakest conjugate base. I don't know if that made any sense to you guys. I know leaving groups is going to be kind of tricky as far as what's the most effective. Typically, you look at basicity. That's how we were able to knock this out, because it's hydroxide and that's a strong base. Strong bases do not make good leaving groups. Weak bases make good leaving groups. And then this one has resonance, which makes it more stable, which is always going to be preferred. Okay. How many would be considered polar protic solvents? Okay, what did we say about polar protic? It can hydrogen bond. So this one. Let's look at these. Yeah, that's it. This cannot hydrogen bond. This cannot hydrogen bond. And this cannot hydrogen bond. Doesn't have any hydrogens to donate. Oh, I kind of like the way that one looked. So that's pretty fast, right? You got an OH. Where do we say? OH. NH. What else was it? Even ROH. Which actually is what this is. ROH. I think. Yeah, and FH. So if you don't see anything like this, can't hydrogen bond, isn't polar protic. So 2. And it's only these 2. Ooh, okay, on a roll. What can be inferred about the transition state of a one-step, highly endothermic reaction? Okay, so I didn't talk about endothermic versus exothermic. So I apologize for that. But what we're going to be looking at really, because it's the transition state, which on a map like that is going to be like this, right? So this is what we're looking at. One step, so it's got one hump. Highly endothermic, so our products are higher than our reactants. Okay, so this is the let me make it bigger. We're going to break this down together, as far as how we're looking at it, what we're thinking about when we look at it, right? So let's draw it. When you see this question, draw it. Transition state, we know from looking over here, is the hump, right? So it's one step, meaning it's one hump. Our reactants are going to start here. We've got one hump, and it's endothermic, meaning the reaction absorbed energy. So that means our products is going to be higher than our reactants. You see that? Higher than our reactants. So if this is the transition state, right? It's asking, is it reactant-like, product-like, intermediate-like? Intermediate-like doesn't even make sense, okay? Because the intermediate is like the in-between. It's the halfway, right? Can't be inferred. You can. I'm telling you right now, you can infer based on this. Okay. So, if we're looking at this, where is the transition state closer to? Closer to our products, right? And if it's closer to our products, that means it is more product-like than our reactants, okay? So when you're looking at these, the main things to look at is one step, okay, highly endothermic. These are going to be the main things. Endothermic, right? That let us know that our products absorbed energy, so it was higher than our reactants, right? Did you guys see that? That was the most important thing about this problem, was that it was endothermic, so our product was going to be higher than our reactants, meaning our transition state is closer to our products than our reactants. So our answer is D, because we are product-like. And it's D. Perfect. Okay, now we're getting into the actual reactants, which is perfect. Reactions, I should say. So this is our rate laws, okay? What did we say SN2 was? What kind of rate was it? Second order, right? It's a second order rate law. What do we care about in the rate of an SN2 reaction? We care about the alkyl halide and we care about the nucleophile. What about SN1? What kind of order is it? First order. You guys are so smart. So proud of you guys. First order. What is the rate of an SN1 reaction? That's right. It's just the alkyl halide. We talked about that extensively earlier. Okay, now we know that. We know what SN2 is. We know what SN1 is. We just have to determine what kind of reaction we're looking at. So these are our products. We're not really concerned about those in this particular problem. Okay, we're concerned about our reactants. So, where is our nucleophile? And where is our alkyl halide? Yes, this is our alkyl halide. How'd you know that? Because you saw a halide. You saw iodine. Good job. Give me 1 second, guys. Okay. So you saw iodine. which is a halogen, which lets you know that this was our alkyl halide, right? So we've got iodine bonded to a single carbon. Now, what does that look like? A methyl, right? Because if this leaves, it's going to be a methyl carbocation. Now, does that seem like something stable enough to exist? Or do we think maybe this reaction has to happen simultaneously because this is not stable enough to exist? A CH3 carbocation, a methyl carbocation, is not stable enough to exist on its own. So does it have to happen simultaneously, or can it exist on its own and stand there for a bit while the nucleophile attaches? It cannot exist on its own. It's not stable enough. So that lets us know that this is SN2 because it has to happen simultaneously. However you spell that. Simultaneously. Has to happen at the same time. Now, as far as, let's further dissect this problem. I want you guys to be able to recognize everything. This is our nucleophile. Why? Because this is really off on its own, right? You have like sodium chloride and things like that. You're never worried about the sodium. The sodium it creates an ionic bond, right? And when we draw ionic bonds, it's literally just this. And then you'll have an OCCH3, right? And then the negative here. So really what we're worried about is this section of it. This is the nucleophile. Because your oxygen has that negative attached to it, it's the nucleophile. Which is what we saw over here, right? Our oxygen and the CH3s bonded to that methyl. Here's the methyl. But for this particular problem, we weren't really worried about it. We were just worried about the rate. So we found the rate just looking at our reactants. So we know it's SN2. And what did we say about SN2? The alkyl halide and the nucleophile are equally important because it happens simultaneously. So we can go ahead and get rid of these two because these are only first order. And we know SN2 is second order. Okay. These are second order. There's two of them. However, this is talking about the leaving group. We don't really care about that. Okay. Was our answer? A. Perfect. A. All right, 4 more questions. Let's knock these out. How many of the following carbocations could be intermediates in SN1 reactions? So, what did we say about SN1 reactions? The carbocation is stable enough to exist on its own. So we're looking for secondary and tertiary, right? Because we were looking for secondary and tertiary alkyl halides. Because once the halide jumps ship, you're just going to be left with secondary and tertiary alkyl group, or carbocation, right? Okay, so let's look. Starting at this one, what kind of carbocation is this? Primary. We're looking at this carbon here, right? And it's only connected to one carbon. This is primary. So it can't be this. That's wickedly unstable. Okay. Good enough. All right. Let's look at this one. What is this? Tertiary. We're looking at this carbon here, and it's connected to 3. Good job, guys. What is this one? Secondary. Good job. Connected to 2 carbons. And this is not a thing. It's in a double bond. This is an allylic carbocation, which does not do SN2 reactions. We didn't even talk about that. Okay. So now what are we looking at? A secondary and a tertiary. And there was 2 of them. B. Perfect. Okay. How many of the following chlorides can undergo an SN2 reaction? What kind of alkyl halides do we want for SN2? We want a blank and a blank. Perfect. Primary, secondary. And also methyl. We'll toss that in there. Methyl is going to be super fast, right? Okay. What kind of alkyl halide is this? Good. Tertiary, because the carbon that the chlorine is attached to is bonded to 3 carbons. I hope you guys are seeing this. This is a tertiary. And not what we're looking for. What is this? Good. Methyl. Literally only 1 carbon involved. What is this? Technically, we could say it's secondary, right? It's bonded to 2, technically. However, like I just said, there's double bonds involved. We never talked about that. We do not do chemistry with this. And the reason why is because benzene is an aromatic ring, right? It's so ridiculously stable, it's not going to want to be doing reactions. It's chill being what it is. What is this? Primary, good. Because the carbon that this is attached to is only attached to 1 other carbon. Primary. Perfect. So how many did we have? Only 2, which is starting to be a common theme. B. Good. Almost done, guys. Stick with me, stick with me. All right. Now, remember I told you it's going to ask for like the best description of the final product. So let's look at this. This bromine. What kind of alkyl halide is this? Yes. Secondary. All right, now we're tricky. Because it's a secondary. Secondary can be either SN1 or SN2, right? So now we have to look over here at our solvents, right? This is our nucleophile. Positive, negative. Okay. Cyanide. Personally, I'm not very familiar with that base. If it's strong or weak. If you guys are, then, that can kind of help you out. Because SN2 uses, like, stronger nucleophiles than weak, right? SN1 uses weaker nucleophiles. So, if it's a very weak base, it's a strong nucleophile. And that would help you out. I'm not familiar with the basicity of it. So, I'm going to look at our solvent. Okay? This is the solvent. DMSO cannot hydrogen bond. right? It's also a really good one to memorize because it's going to be used for aprotic. It's an aprotic solvent. That's just something to memorize. When you see DMSO, it's aprotic, okay? And what uses polar aprotic solvents? SN2. Okay, so now we're looking at the product, right? So this started out as, let's check the stereochemistry here. This is obviously priority 1. Here, I'll do it in a different color. This is priority 1. This is priority 2, because this carbon is bonded to another carbon. This is priority 3, and then our bolded hydrogen will be priority 4. Okay, so it looks like we would be going this way. However, priority 4 is in the front, so we need to flip it. And we're actually going to go this way. All right, you guys remember that? So we're moving clockwise, so we are R. Okay, it's an SN2 reaction. Which what? What did we talk about? What? It's a backside attack that inverts stereochemistry. You guys remember me talking about that? So, if it used to be R, that means this one's going to be S, which we didn't talk about, or it's not showing you, right? He's not going to show you dotted or not because that would give the answer to you. That's why it's on a line. But this is still a stereocenter, so that means it has to have an orientation. So it did a backside attack as far as like this did, right? It did a backside attack. And it inverted our stereochemistry. So we're now S configured. And that is C. C. Okay. I hope that made sense. There's a lot of rules to memorize as far as the chemistry goes. And it's a lot. There's a lot to it. But SN2 inverts the stereochemistry because it does a backside attack. So think of it if it's, I'll draw it like this. We've got 4 carbons. 4 carbons. Here's where the bromine is. And so the hydrogen is bolded, right? The CN is going to hit it here, and it's going to cause, well, that's going to pop off. And then it ends up giving you I feel like that wasn't a very good drawing. I'm not sure how to, like, draw it out for you guys. I apologize. But it, basically, think of it as it, like, rams it so hard that it inverts it. Like, it flips it backwards. That's how I, like, used to think about it. But I'm saying it out loud, and it's not making a lot of sense. So I'm sorry. Okay, so this is an SN1 reaction. What would best describe the nature of the carbocation intermediate? Okay, so I feel like this was this is a definition question, and I don't think I really covered that. This is chapter 7. Nomenclature, leaving groups, solvents. Oh, here's DMSO. Aprotic, dissolves. So DMSO, DMF, those are ones to remember that they're aprotic. Inversion of it. SN1. Okay. So that wasn't helpful. Sorry, guys. Let's go look at this. Okay. So the carbocation intermediate. I'm trying to remember. I feel like well, let's just draw it. Okay. So we know that the bromine is going to leave, right? That's the first step. So then we're left with this. CH3. CH3. Okay, so we know it's not achiral because it's not a meso compound. Right? Do you guys see why? We can go through it all. We got 2 stereocenters. Well, right now we only have one. Right, we only have one stereocenter. Right here. And an achiral would be no stereocenters or 2 of them, and they're meso compounds, so it's like, what's it called? When it you put it over top of itself and it's exactly the same. Gosh, there's the word for it and I'm blanking. I keep thinking disposable. Superimposable. There it goes. It's non-superimposable, or achiral would be superimposable with 2 stereocenters, but right now we only have one. Because this is missing a bond, right? This is a carbocation. So it's not that. A mixture of diastereomers. Well, it's not a diastereomer because we only have one stereocenter, right? Racemic, we don't know. Because we don't have both enantiomers. So racemic would be that we have both enantiomers and they exist at the same amount, right? 50-50. However, it could be a single enantiomer because we only have one. Does that make sense? That's like the best answer out of the bunch. It's kind of a weird question. I don't remember really getting that, but that was just the best answer I saw out of the choices we had. So hopefully you don't get a weird question like that on your homework. And if you do, text me and hopefully I can just do what I did here and just pick what sounds the best to me. And I can't really explain why, but I'm sure you guys will be okay. All right, so that was everything, the homework, the chapter. Let me know if you guys have any other questions about it, and good luck on your homework.